So we proved the existence of a splitting field. Let me actually talk about the uniqueness a little bit, part B of this theorem down here. And I won't go through the whole proof, rather subtle, but at least I want to talk about this lemma about extending homomorphisms of fields or extending embeddings of fields that goes into the proof, because this sort of shows up time and again, and also the argument that proves this lemma is sort of important for the later development of things. So let me explain the statement. You have an embedding of fields M to L, means an injective homomorphism, preserves addition and multiplication. Actually, even before I explain the statement, I want to make one remark that whenever you have even a ring homomorphism between two rings, you can extend it naturally to the polynomial rings. Simply by applying sigma to the coefficients. If you take a polynomial here, I'm just going to send it to sigma mi x to the I. So I'm not going to touch the variable, I'm just going to apply sigma to the coefficients. And you can check that if sigma is a homomorphism, then this is also a homomorphism. And I'm going to also call it sigma. Slight abuse of notation. Now let's read the lemma. So you're given embedding of fields from one field M to another field L, and you want to know when it can be extended, I'll explain what that means, to a bigger field K that can be obtained by adding a root of some irreducible polynomial Q. So take a irreducible polynomial Q in Mx, then you get a bigger field, Mx mod Q. You can put M inside there, right? We have learned that. The question is, when does there exist a sigma bar from K to L such that its restriction to M is your old sigma? And the answer is, the lemma says that sigma extends to K, so the answer is yes, if and only if the polynomial sigma qx has a root in L. So sigma q just means take the polynomial q, it's a polynomial here, and apply sigma to the coefficients. So if q is some ci x to the I, sigma q is sigma ci x to the I. If this thing has a root in L. Okay. Let me explain why this is so. So first note that I can suddenly, so I want to extend this sigma to this quotient of a polynomial ring. But if you want to define a map from the quotient of the polynomial ring, first you should define a homomorphism from the polynomial ring itself. M does sit in there. So let's see, what do I need to do to get a map here? Well, all I need to do is just choose an element of L. You see, I already know what to do to M. A typical polynomial looks like this. So if you want to define a homomorphism, you already know that the mi's are going to go to sigma mi. Let me choose a different color so we know. So you take a polynomial, you know that mi goes to sigma mi. So you just have to tell me where x goes. So let's say x goes to some element b. Then x to the I goes to b to the I. then this polynomial goes to that polynomial. So it certainly extends here, and all you need to do is just choose an element, and basically, so you have this inclusion and sigma, and then you compose with the evaluation at B map. So the sigma twiddle is really sigma followed by evaluation. This sigma followed by evaluation at B. That sigma. Okay. Now the question is, when do I get a map sigma bar down here? Now, of course, from mx to this quotient, you have the quotient map. So you should try to apply the first isomorphism theorem. So there exists. So the question is, does there exist sigma bar from K to L such that sigma bar restricted to M is sigma, which is same as saying when is there a homomorphism from K to L such that applying pi and then applying sigma bar is same as applying sigma twiddle. So what is the condition? When does, so let's ask a slightly different question. When do there exist, or does there exist, such that sigma bar followed by pi is your sigma twiddle? These are really the same question. And I know the answer to this. The answer is if and only if this polynomial is in the kernel of sigma tilde. That's what first isomorphism theorem tells you. So what does that mean? Let's compute. What does this mean? This means, so if and only if this. So there exists sigma bar from K to L such that this happens if and only if Qx is in the kernel of sigma tilde. What is sigma tilde of Qx? If I write Qx, I already wrote Qx, I suppose, like this. So this is sigma tilde of Qx. And that's equal to sigma tilde applied to Ci is just sigma Ci. And sigma tilde of x is b, let's say. So this is b to the power I. But notice that this is same as the polynomial sigma q evaluated at b. See, sigma q is this polynomial. So evaluate it at b, you get this. Sigma Ci b to the pi sum. So then when is q in the kernel of sigma tilde? Exactly when this is 0. Exactly when sigma q of b is 0. This is if and only if sigma q of b is 0. That means you have to, if you have to factor through this k, as we say, the sigma twiddle has to send x to a root of sigma q. So sigma twiddle factors through k if and only if sigma x equals b is a root of sigma q. And that's essentially the proof. So if you have a root of this polynomial available in L, then you can send x to that guy, and then you'll get a homomorphism here, and then you just check that, so then you get a sigma twiddle here, and then you just checked that because b is a root of this polynomial, the polynomial q is in the kernel of sigma tilde, then by first isomorphism theorem, you'll get a map here. Conversely, if you have a map here, then you had just checked that the image of x under sigma tilde has to be a root of sigma q. Okay. Another way to say this would be to note that k is really m adjoin a root of q. So this is a root of q. You wanted a sigma bar. You already know what you have to do to the elements of M. You have to apply sigma to them. So the question is, where do you send A? Well, A is a root of Q, so you have to send A to some B, which is a root of sigma Q. So this has to be a root of sigma Q. That's the point. Alright, so on with this, let me try to quickly explain how the uniqueness of splitting field go. So you have K and K prime, two splitting fields of a polynomial Px over F. And you want to show that they're isomorphic. So what you do is you take the inclusion map here, and you have K containing F, and you want to extend this I prime to an embedding from K to K prime. If you can extend it to a homomorphism, you can show rather easily that it actually has to be an isomorphism. So the plan is to actually extend it as far as you can. So what you do is you extend it as far as you can, meaning choose field M such that M is between F and K, such that there exists a homomorphism from M to K prime extending I prime. So its restriction to F is I prime. And third, that it's as big as possible. We are talking about splitting field of a single extension here, so all these extensions are finite. So I just want this dimension to be as big as possible, subject to the other conditions. And then the claim is that this M has to be K. That if you extend it as far as possible, then you have already extended all the way. And the point is that if it is not, then there is some root of Px that is not yet in M, because K is just obtained from F by adding all the roots of P. So it must be there is some root that you haven't added yet. So let's say Qx is the minimal polynomial A in Mx. Now I can add that and I get a bigger field. And I know this field is isomorphic to Mx mod Q. Now note, Q is a minimal polynomial of A. A is a root of P, so Q divides P. And that implies, actually, that sigma Q divides sigma P, but P has coefficients in F, and sigma restricted to F is just inclusion, so this is just P. So sigma Q actually divides P, this polynomial sigma Q. And K prime is a splitting field of P, so it has all roots of P. So it has a root of sigma Q. Because sigma Q, after all, is a factor of P. And now my lemma kicks in, the lemma up here. I have a sigma, and the polynomial sigma Q has a root in this field, so I can extend it here. So extends by lemma, and that contradicts maximality of M. That's a proof in the nutshell. So M has to be actually K.